Everyone good with the example?
Yes, sir.
Yes,
Yes,
sir.
sir.
Who's not finished with the examples as yet? Like I said earlier, we'll be mostly looking at the 2 by 2 matrix. But that does not mean that we would not get a different matrix coming into the mix, right? But then you have to remember certain specific rules. What are the rules so far when we're adding and subtracting?
Um, first, in
What have
addition,
you noticed with the elements of matrix A and the elements of matrix B?
Can you repeat, sir?
Okay?
Yeah, repeat.
Matrix A is a 2 by 2 and matrix B is a 2 by 2, sir.
But it's a 2 by 2. Both of them are 2 by 2, which means that we can only add and subtract matrices that have the same order in terms of rows and columns. So once the rows and the columns for whatever matrix you're adding or subtracting, they're not the same, it means that we cannot go forward with working them out or solving them. Please make that note in your exercise book. Please make that note.
sir, please repeat, please.
Did you hear that?
Can you please repeat what you
Okay,
said just now?
I was saying that we add matrix A to matrix B, we subtract matrix A and matrix B because they have the same order. In terms of order, I mean that they both are 2 by 2 matrices. They're both 2 by 2 matrix. So once you have the same order, you can add and you can subtract. Is that clear?
Yes,
Yes,
sir.
sir.
Clear.
Everybody good?
Yes, sir.
Yes,
Can we
sir.
move
Yes,
on
sir.
now?
Yeah. You can move on like a dart. Oh, wait, I'm unmuted.
Good. Look at what is going on here. Tell me what is going on here. We have A plus C and C minus B.
Sir, we got 2 by 2 matrices and a 3 by 2.
Let me get that.
You got 2 by 2 and a
And what kind of matrix is C?
and 3 by 2.
Everybody agree?
Yes, sir.
Yeah.
So matrix A is 2 by 2, while matrix C is 3 by 2. So can we do the addition or the subtraction there?
No, sir.
Oh,
No. Therefore means that we cannot get an answer for that. Even if we try, 3 might add it to 3, negative 2 to 0, and 0 to negative 4, 8 to 19, but what will happen with 7 and 8? 7 and 8 will remain by itself, which means that for this here, we cannot get any answer. So this is not possible. No answer possible. What about C minus B?
Sir, the same thing. There's no answer possible.
Same principle applies, sir.
Sir, you won't get no answer.
Ah,
You would not get any answer.
but again, we will not get any answer because the two matrices that we have there, they do not have the same order in terms of rows and column. So again, this here is out. Right? So this is something that you need to pay attention to. It can trick you up later on. Are we good there?
Yes,
Yes,
sir.
sir.
Yeah.
We're on to the multiplication. We'll be looking at scalar multiplication. Now, a scalar would just represent, a scalar just simply means any given quantity. So if you look, given the matrix A, B, and C, find 3A, find 2B, find 2C minus A, find A plus B minus 2C. For the first example, 3A, what have you noticed there?
The 2 by 2 factor. It is different.
Our scalar value in this case would be 3. So what it simply means is that the scalar multiplies by all of the elements within our given matrix.
Excuse me,
So we
sir.
have 3 multiplied by 3 give you 9, 3 by 0, 0, 3 by -2, and 3 by 8 give you 24.
Excuse me, sir.
Huh?
The number outside the bracket is always a scalar.
I didn't hear you.
The number outside the bracket is always a scalar.
Yes, the number outside the bracket is known as the scalar quantity.
Thank you, sir.
For the second example where we have 2b, you notice that the same thing was done. 2 multiplied by everything inside the bracket. 2 by -4, 2 by -7, 2 by 10, 2 by 15. For example 3, you'll notice we have a combination of operations. So while we do the scalar multiplication, we still have to do a subtraction there. Please copy the given examples and make your notes. Please make your notes at the side of the examples that you copy. Any other questions? Any other questions, anybody? Check out the last example. A plus B minus 2C. Are we good with this example?
Just now, sir.
You will notice here the first thing we did was remove the scalar. We did the scalar operation, which is 2 by 6, 2 by 9, 2 by 2, and 2 by 11. And we set it down there. Now, the reason I didn't do the addition first and then the subtraction, or the subtraction first and then the addition, is because regardless of what you do, how you do it, you will get back the same answer. So you can actually try adding the first 2 matrices, and the answer you get, you subtract it from the last one. Or you can try subtracting the last 2 matrices and then adding your answer to the first one. See if you get back the same thing. Everybody got there?
Yes, sir.
You tried it both ways. Did you get back the same answer?
Yes, sir.
Everybody got there?
Yes, sir.
Yes, sir. Yes, sir.
Ready?
Yes, sir.
Can we move on? Good. So we'll be looking at the adjoint of a 2 by 2 matrix. Now you will only need to use the adjoint when you're finding the inverse of a matrix. All right, we will do the adjoint. Yes, we use the adjoint when we have to find the inverse of a matrix. Now, if you look at the screen, if you look at the example, the very first line, I have a matrix M, A, B, C, D, and the adjoint of M, you notice some changes there. The first thing you notice is that we had a change, we have a change. We have a change because B and A would have switched position. Right? And what have you noticed with C and D?
They became negative.
I didn't get that.
The value
They
change.
became negative.
They became negative. No, they did not really become negative, as you will see from the 2 examples at the bottom, but they become the inverse of their sign. Inverse would mean opposite, right? So you can make
Yes,
a
sir.
note of that. For the adjoint, our leading diagonal, which is AD, the 2 values switch places. So A takes the place of D, and D takes the place of A. For our non-leading diagonal, which is B and C, they become the inverse. Inverse meaning that if the values were positive, they both become negative. If the values were negative, they both become positive.
Excuse me, sir. Just the first and the last number just switch place?
Yes, just the first and the last number switches place. As you can see from the arrow, that the diagram that I have there, the arrow, only those two numbers switch places. While the other two values, they become the inverse of each other. So look at the first example. We have find the adjoint of the 2 by 2 matrix 6, 5, 4, 3. You'll notice here for the adjoint, what happened with the 6 and the 3? The 6 and the 3 switch places here. And the positive 5 and the negative positive 4 becomes negative 5 and negative 4. Check out the second matrix.
Sir,
Huh?
since 14 is a negative, when it inverts, it becomes a positive.
Exactly. So you notice for the first example, positive 4 and positive 5, for the adjoint, they both become negative. For the second example, the negative 14 became positive. Now, why didn't we change anything on the 0? Why didn't the 0 become a negative 0?
Because 0 is 0. It cannot be changed.
I didn't get that.
It has no value.
Repeat.
It has no value.
0 is neutral.
Neutral.
0 does not carry positive or negative. Are we good?
Yes, sir.
Yes, sir.
Please copy the examples and make your notes. Everyone good here?
Yes, sir.
Yes, sir. Yes, sir.
But look at our determinant now. The determinant is another part that is used also to find the inverse of a matrix. Now you'll notice that the determinant carries a different operation as the adjoint. For the determinant, for the adjoint, just now we switch the leading diagonal and we change the value, the inverse, the non-leading diagonal, the value becomes the inverse. For the determinant, you notice that we do a cross multiplication, A multiplied by B, and B multiplied by C, and we subtract. So we always set it down like this. A multiplied by B always goes to the front.
So, sir, every time you're using determinant of a matrix, the M or any other letter is always being single line brackets.
I didn't hear that.
What about the M in the single line brackets?
What about the M?
Yes, sir.
The M is just the name of the matrix.
No,
And
sir.
this
I'm talking about the M. Sir,
in
I'm talking about the one with the line.
I didn't hear that.
I'm talking about the one with the line.
Oh, you're talking about this here?
Yes, sir.
That is how it's represented. So you may either find the determinant of, look, I have the example here. You have find the determinant of A, or they can tell you to determine just this only, which you should understand that this here is talking about the determinant.
Okay, sir.
Is that clear?
Yes, sir.
On Friday when
Yes,
we
sir.
our next class, when we do the exam paper, a question from the exam paper, you will see all of these things. They're just different ways in which they ask you to find the determinant. So you have to familiarize yourself with the symbol as well. But if we go to the first example, you'll notice the determinant of A. Again, like I said, we multiply. 12 multiplied by 2, 3 multiplied by 2, and we subtract. For our third example, Second example, sorry. I'm hoping that everybody is familiar with what is going on between here.
Sir, one of the sign mean minus and one of the sign mean negative, right?
Repeat?
One of the sign mean minus and one of the sign mean negative, right?
Yes. So what you have there is 2 minus negative 12. But in terms of the operation, remember the first rule that we should have learned is that a negative multiplied by a negative would give you what?
A positive.
A negative multiplied by a negative would always give you a positive. So this same rule here is what is being applied here. Any other questions? Are we good there, folks?
Yes, sir.
Yeah.
But now, for the determinant of a matrix, we have something known as the singular matrix and the non-singular matrix. The singular matrix is a matrix where the determinant is equal to 0. And as you can see here, this is how we find the determinant. All right, that is how we find the determinant. And once we get a value of 0, it tells us that our matrix, is a singular matrix, which means that it does not have any inverse. Let me go that again. A singular matrix is a matrix where the determinant is equal to 0. In other words, that matrix does not have any inverse. Is that clear?
Yes, sir.
Take a note of that. I will repeat it. A singular matrix is a matrix where the determinant is equal to 0, which means that that matrix does not have an inverse. Are we good there, folks?
Yeah.
And you have the 2 examples there. 2, 3, 4, 6, 6, negative 2, 3, negative 1. Please copy the 2 examples. Everyone go with the examples. I'm not hearing persons from that is here, that are here. Everybody answering me.
Let me finish it.
Repeat?
I'm not finishing.
Yeah, take your time. Again, please ensure that you make your notes at the side of each piece of working. Any questions so far? Everybody good there?
Yes, sir.
So
Yes, sir.
Let me ask this question now. If a singular matrix, the determinant is 0, what would happen with a non-singular matrix?
Sir, I don't think it would change.
Would change? Huh?
Sir, please repeat the question.
The singular matrix have the determinant equal to 0. So what would be a non-singular matrix? Anybody? What would be a non-singular matrix? Obviously, you should know that a singular matrix is the opposite of a non-singular matrix.
Or not equal
So,
to 0.
if for a singular matrix you can only get 0, it means that for a non-singular matrix, any value that you get other than 0 would prove to you that your matrix is a non-singular matrix. Let me go that again. For a singular matrix, you can only get a determinant of 0. For a non-singular matrix, any other value that you get, I'm talking about from 0.1 all the way to a million and negative 0.1 all the way to negative 1 million. So once you get any other value other than 0, you have a non-singular matrix. Is that clear?
Yes, sir.
Any other value other than 0, your matrix is a non-singular matrix. And for non-singular matrix, they have inverse. Moving on.
Yes, sir.
Any questions?
Yes, sir. Yes, sir.
So if we to recap, we would have looked at the addition, subtraction, scalar multiplication, adjoint, determinant, and singular matrix. Remember the rules for addition and subtraction, as well as the rule for scalar, adjoint, and singular matrix. Please copy and complete. So take your time, copy the questions. For the first example, you can work number 1 and number 2. For the first question, sorry, you can work number 1 and number 2. For the second question, you can work out M. And for the last question, you can work out A and C. And I will choose person's screen for them to share the answers. You have about 10 to 12 minutes to get those 1, 2, 3, 4, 5 questions done.
Sir, how much is if you do for the first one?
Repeat?
For the first one is which set you doing first?
Just do 1 and 2.
Alright, thanks.
For the second set, you just do M. And for the third set, you're going to do A and C.